right, what's up, everyone? Welcome back. Today we're talking about positive operators. So, positive operators, what's the deal with a positive operator? Well, here's the gist of it. It's not too complicated. We're basically just categorizing further self-adjoint operators. So, an operator T on an inner product space V is said to be positive if it's self-adjoint and the inner product of the image of V with itself is always greater than or equal to 0 for all V and V. Okay, what's going on here? Well, let's think about a few things. Let's make a note really quick. So just a fast little note, something to remember. All right. Be careful not to make a mistake and forget that if you're over C, then let me write this. Okay. If V is an inner product space, over the complexes, then we can drop the requirement that T is self-adjoint, since having TV inner product V in R, terrible R right there, for all V in V implies this in that case. So we proved this back when we were talking about self-adjoint operators. In particular, we said, hey, look, if the inner product of the image of something under an operator with the thing you put into the operator is real for every single possible vector, then we get self-adjointness. Okay, so nothing too crazy. Fair enough. This is an important thing, though, because of the following reason. So be careful. To not make a mistake and forget this. That is, C doesn't have a less than or equal to like R does. Okay, now that I'm done writing this long thing while talking slowly, let me kind of say something more about it. So the important piece here is that, hey, if you've got V in inner product space over C, then you can drop the requirement that T is self-adjoint, since having TVV inner product right there, real for all V, says that T is indeed self-adjoint. But the important thing to remember, the big deal here, is that if you forget that this inner product right there, this TV inner product with itself, is in the reals, then you'll make a mistake, because the complex numbers don't have a nice ordering the same way the real numbers do. I mean, I'm not saying you can't put any ordering on the complex numbers, but they don't have the same kind of nice ordering that the reals do. Just think about the fact that the complex numbers are basically just two copies of the reals, right? Have you ever seen a nice ordering on R2 that has the same properties as an ordering on R? No way. You'd have to do some sort of a silly thing, like think about the distance from 0 of a real number in R2 or a vector in R2, and then try to use some sort of an ordering like that. But then that gives like a whole bunch of things who have the same distance from 0, but you take their difference and you don't get 0. So you don't have a lot of the nice properties that the regular old less than or equals to sign in the reals has. So just don't forget this. If you forget it, then you'll end up making mistakes, because you'll be assuming that this thing is like a complex number when it's really a real number, and the complex numbers don't have this nice ordering. Okay, fair enough. Enough about that. So this will be closely tied to something called the square root of an operator. Positivity will let us select a unique square root. That is essentially the whole idea of this. So an operator is called a square root of an operator if you square it and you get back that operator. So r is a square root of t if r squared is equal to t. Let me give you a quick example. Something easy. Okay, let's let t be a linear map from f3 to itself for any field f. Let it be defined by t x1, x2, x3 equals x3, 0, 0. Okay, certainly this sends 0 to 0. You take a scalar multiple of the inputs, you get a scalar multiple of the outputs, bada boom. All right, let's let r in LF3 be r of x1, x2, x3 is just, I'm going to shift it over just a little bit less, x2, x3, 0. Then r squared of x1, x2, x3, well, this means I apply r to the result of r of x1, x2, x3, which is x2, x3, 0. But when I apply r to something, I just shift the last two entries over 1 and fill the last slot with 0. So now I shift the last two entries, which is x3 and 0, over 1, and I fill the last slot with 0. So I'll get x3, 0, and then another 0. Oh, but hey, wouldn't you know it? That's t of x1, x2, x3. So r squared is equal to t, and r is a square root of t. Is this unique? Well, just think about it really quick. So what could I do? Maybe I could mess this up somehow. For instance, consider if you take r prime of x1, x2, x3, and that's a prime, like a little apostrophe, not like a 1, to be just r of x1, x2, x3, but now I'm going to make things negative. Then r prime squared of x1, x2, x3, well, I just apply r prime to the result of r prime of x1, x2, x3. So I have r prime applied to negative x2, negative x3, 0. All that happens is I shift over and flip signs. So I'll get x3, 0, 0, which notice is t of x1, x2, x3. So r prime is a square root of t as well. It's not hard to come up with more of them. There are plenty of them. So this is an important thing to notice. Square roots are not unique. They're not even unique in the reals, right? If you take a square root in the reals, you get a positive and a negative solution. Similarly, look, we could take a square root of an operator t, and we could just take negative that operator, and that was also a square root. Ooh, this is a problem. Maybe this makes some sense of why we would talk about an operator being positive. That is, if we want to take like the positive square root of a number, then that's well defined. That gives you a specific actual number if there is a square root of it, you know. If you take the square root of 2, you get plus or minus square root 2 as your answer, right? Well, those are the things that you can square to get 2. Okay, but if you pick just the positive solution, then you've uniquely specified a particular number. This is the same idea here. We're going to say, hey, when do operators have square roots, and how can we specify them uniquely? So let's get into it. Okay, so positive operators. Let's prove a few facts about them. And let's get into talking a little bit more about square roots. So, first one first. We're going to go through and we're just going to do this huge, long laundry list of equivalences. The first one, as you might imagine, is that t is a positive operator. Then we're going to show that that is equivalent to a whole lot of other things. Our proof strategy will just go in a big old circle. We'll show that A implies B, and B implies C, and C implies D, and D implies E, and E implies F, and F in turn implies A. So let's start it out with A implies B. So to get A from A to B, all we have to do is the following. So I would say that a positive operator is self-adjoint, is immediate from the definition. Okay, after all, positive operators is self-adjoint operators such that the inner product of TV with V is always greater than or equal to 0. Okay, cool. So that's fine. Okay, now all we have to do is show that the eigenvalues of T are non-negative. Okay, so suppose T is positive and lambda is an eigenvalue of T with eigenvector V. Okay, then watch this. Okay, here's how we're going to build to it. So 0 less than or equal to inner product of TV with V. That's positivity. Okay, now this is equal to a lambda V, inner product with V. And that's equal to lambda norm V squared. So notice lambda has to be, well, non-negative. After all, lambda norm V squared is greater than or equal to 0. This part is bigger than or equal to 0. So that part certainly couldn't be smaller than 0, right? All right, easy enough. Now let's do B implies C. Okay. B implies C. So this claim that if T is self-adjoint with all eigenvalues non-negative with respect to some basis of orthonormal vectors, the matrix of T is diagonal with only non-negative numbers on the diagonal. This is immediate from the spectral theorem. So I'll just write spectral theorem. That is, we've got a self-adjoint operator, and with respect to some orthonormal basis, from the spectral theorem, we know that it has a diagonal matrix. All right, then after all, the entries on the diagonal here will all be eigenvalues, which we've assumed are non-negative. So that's just the consequence immediately of the non-negative assumption, or the non-negativity assumption on our eigenvalues. Easy enough. So B implies C, spectral. Okay, let's do C implies D. Okay, C implies D. So by the linear map lemma, here's the idea. We're going to take an orthonormal basis of V such that the matrix of T is diagonal with only non-negative numbers on the diagonal. Okay. There is a map R in LV such that, here's what I'm going to say. I'm going to say, okay, such that R of EK is equal to the square root of lambda K EK, where E1 through En is the assumed orthonormal basis of V such that MT is diagonal with lambda k, its kth diagonal entry. Oh, okay, fair enough. Now, certainly, r is positive, I claim. Why? Well, let's just show it. Take r, ek, inner product ek. What am I going to get? I will get the square root of lambda k, ek, Perhaps I'm skipping one step right there where I write the square root of lambda k inside of that angled bracket, inside of the inner product. But this is just square root lambda k, since this is an orthonormal basis and this is the norm of ek squared. Bam. All right. So, moreover, r squared ek, that's equal to, well, I'll get lambda k. I guess I'll put the square root there and then square it, ek, but that's just lambda k, ek, which notice is just t, ek. So, t equals r squared. That is, r is a square root. Oh, cool. Wait, why did we do all of this just with EKs? So maybe I should have said that as we were going through it. The reason is because this is a basis. So if we can show that everything holds on a basis, then it holds for other non-basis elements just by linearity. So that is, instead of doing RV inner product with V, we'll just do REK inner product with EK. Since after all, if you take RV inner product with V, you can just split up those V's into linear combinations of E1 through En. And then if you split everything apart, it'll just turn into a lot of pieces that look like this. So that is, having a property for some linear map, it is enough to show that the property holds on a basis. All right, cool. So we showed that if with respect to some orthonormal basis of V, the matrix of T has a diagonal is diagonal with only non-negative numbers on the diagonal, then T has a positive square root. Okay, cool. Now let's assume that T has a positive square root and show that it has a self-adjoint square root. So D implies E. Okay. So this is almost so easy that it seems sort of strange to say. Positive square root, self-adjoint square root. Well, positive operators are self-adjoint. Okay. Let's do E implies F. All right. Now what we want to say is that if we've got a self-adjoint square root, then T is equal to R's adjoint times R for some R. Okay, let's prove that. Suppose T equals R squared and R is self-adjoint. Then R equals R star, so R squared equals R star R, which R squared is equal to T. And we're done. That is, we showed if T is a self-adjoint square root, then T is equal to R star R. R adjoint R. Okay. Now let's suppose that T is equal to R adjoint R for some R, and let's show that T is then positive. So let's show that F implies A. So, suppose that T equals R star R, then T star, what's equal to R star times R star star, which is R star R, which notice is equal to T. So, T is self-adjoint. Now, let's show that it's positive. Whoa, my tablet is lagging out. Moreover, TV, inner product with V, well, it's equal to R star R V, inner product with V, which, just using properties of adjoints, how do you flip it over into the second argument? You star it. And if you double star it, it's the same as taking the star off. So we get RV, RV, inner product, which is the norm of RV squared, which is necessarily greater than or equal to 0. So T is positive. We're done. Nice. How about that? That is pretty cool. We did it. Nice. Okay. So, positive operators. A lot of good properties. A pretty long proof right there, but mostly because this theorem just had a lot of different equivalences. All right. Let's go on a little bit further and let's use these positive operators in the way that we first described. That is, to get unique square roots. Okay, let's prove it. So, what we're going to show is that every positive operator on V has a unique positive square root. Here's the proof. All right, first off, let's just write what we got. So, suppose T in LV is a positive operator. Okay, let R be a positive square root of T. Which we know exists by the previous theorem. We show uniqueness. That is, we just went through and said, hey, look, if T's a positive operator, it has a positive square root. Absolutely true. All right, we've showed that. Now, what we're claiming is that every positive operator has a unique positive square root. We already knew it had a positive square root, so we have to show uniqueness. So, let lambda be an eigenvalue of T with eigenvector V. Okay, we will show that RV is equal to the square root of lambda times V, which shows R is unique since V has a basis of eigenvectors of T. This is by the spectral theorem, by the way. Okay, so the idea of it is basically saying, hey, look, since T is self-adjoint and since T's positive, right, then we know that there is a positive square root. So since positive operators are self-adjoint, and we know that self-adjoint operators give bases for their space that consist only of eigenvectors of that operator, then V has a basis of eigenvectors of T. And so to show that R is unique, we just have to show that it has find a formula for it relative to eigenvectors of T. That is, if it is uniquely specified on the eigenvectors of T, since they form a basis, it is uniquely specified on all of V. Okay, so let's show it. So that RV is equal to the square root of lambda V is true follows from, let's do this. Well, I'll say it this way. Follows from applying the spectral theorem to R to get a basis of, or I should even say an orthonormal. Let me say it, to get an ONB, orthonormal basis, of eigenvectors of R for V. let E1 through En be this basis. Okay. Since R is positive, there exist lagging tag non-negative lambda 1 through lambda n in the field such that, and in particular the field here is the reals, just to be clear, such that R e k is equal to the square root of lambda k e k. After all, like they're eigenvectors, so they have eigenvalues. Just pick the thing that you square it, and you get that these lambdas are the squares of the eigenvalues of R. Cool, easy enough, right? Okay, there you go. So write our v, which we're calling back here. We're gonna say, hey, remember, let lambda be an eigenvalue of t with eigenvector v. So write v in terms of this new basis as a1 e1 plus dot 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 all the way down through a n e n. Yeah? Okay. Now, since this is a basis, and notice, or since this is a basis, we can do this. So notice that r squared v is now equal to a1 lambda 1 e1 plus dot 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 all the way down through a n lambda n e n. Hence, we get the following. And tv equals lambda v implies, since r is, by our assumption, a positive square root of t, implies that lambda v, which notice is equal to, just by definition, a1 lambda e1 plus dot 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 all the way down through a n lambda e n. Okay, this is equal to t v, which is equal to r squared v, which is equal to a1 lambda 1 e1 plus dot 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 a n lambda n e n. So a1 lambda minus lambda 1 e1 plus dot 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 all the way down through a n lambda minus lambda n e n is equal to 0. And since e1 through en is a basis, if ai is not equal to 0, then lambda is equal to lambda I. Oh. So, whoa. So, RV is equal to A1 lambda E1 plus dot 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 all the way down through AN lambda EN. Since if AI is equal to 0, we can still replace lambda k with lambda here without changing anything. That is, we only needed to show that RV was of this form. Yeah? And then we're set. Cool. That is, this is just lambda v. Whoa. Pretty cool, huh? Pretty cool. Oh, sorry, root lambda v. Oops. This should be root lambda. Right? Yeah. Or should be, I guess, r squared v, but let me just save us that step of doing this. There we go. So, sorry, I forgot to draw some square roots. Totally fine, since we can just, do that anyway. All right, good. Hopefully that didn't throw anyone off that I forgot to write the square roots. But basically the whole idea of it is, hey, if any of these AIs are 0, then we don't actually need to show that lambda is equal to lambda I, because after all, the term contributes nothing. So in those cases, you can still replace it. It's totally fine. All we really needed to show is that if AI is non-zero, that lambda is equal to lambda I, since that's the place where it matters if they aren't the same. Okay, cool. So we did it. We showed uniqueness. That is, we said, hey, you got a positive operator, or you got a positive operator. Cool. We know we get a positive square root. Let's show that that square root is unique. All we'll do is we'll show that it has a certain form on eigenvectors. That is, we have a formula for it acting on an eigenvector. And since by the spectral theorem, V has a basis of eigenvectors, this means that we have a formula for R on a basis of V. Okay, cool. So that gives you a formula for R on all of V. That means R is uniquely specified. Super nice. Let's keep it going and talk a bit more about all of this, finish things off. Okay, to finish things off, no difficult or tricky proofs, just a little bit of notation, a basic fact, and then we'll do an example just to kind of wrap it up, make sure everything's hitting home, okay? So the idea is that if you have t, a positive operator, let's denote by square root t the unique positive square root of t, since after all, as we just showed, there is one and only one such positive square root. Okay, cool. So this tells us nice stuff, like for example, if t is positive and tv inner product v is equal to 0, then tv is equal to 0. This is actually pretty cool. So here's the idea. Let's do the proof of it and also say the actual technical statement instead of just this kind of vague shape of things, kind of picture proof. Whoa, what's going on with my stylus? Interesting. Something's up. Come on. Okay, here we go. All right, sorry, my tablet is being weird on me. Maybe I need to get a new one of these suckers. All right. So, if t is a positive operator, and v is a vector in V such that tv inner product with v is equal to 0, then tv is equal to 0. That is, if v is non-zero and is an eigenvector corresponding to the eigenvalue 0 of t, then tv inner product v is 0 as well. So, kind of interesting, it says that for positive operators, if the image of a vector is orthogonal to that vector, then the image of that vector is 0. Kind of cool. This says that we can kind of rule out the case of like the 90-degree rotation in R2. All right, so let's show it. All right, so take 0. Suppose that's tv inner product with v. Okay, now just write tv as square root t, v, v. Well, since the square root of a positive operator is the unique positive square root, and a positive operator is always self-adjoint, we can just turn this into square root t, square root tv, square root tv, since when we take the adjoint of root t, it is itself. Oh, wait a second. This is the norm of the square root of t applied to v. So, watch this. This says that the square root of t applied to v is equal to 0. Oh, wow. Look at that. Nice. So, from this, thus, if we apply t again to both sides, well, that's the same. Let me be slightly clearer here. Let me move this slightly. All right. That's the same as saying, that tv is equal to, well, it's square root t v, square root t of 0, so 0. Boom. We proved what we wanted. Nice. Easy. So, if t is a positive operator and tv inner product with v is 0, then tv is equal to 0. So kind of a nice little piece there that settles a small technical point I believe we made when talking about the spectral theorem. I don't have it in front of me right now, but in case anyone was wondering about that, there you go. I don't believe that it's actually an issue or anything. But by that, I mean, I don't believe anyone was actually probably thinking about this, but I briefly mentioned this point about TV inner product V being 0. Don't worry about it if you don't remember that comment. It's totally fine. So let's do an example. Let's drive everything home. Let's make sure we're cool talking about square roots. All right. So let's let T be a linear map on R2 be given by T of xy is equal to x plus y, x plus y. Sound good? Okay. Notice that T of xy, T of xy is equal to, well, I've got x plus y, inner product with x plus y, and here I'm just taking the inner product to be the dot product, which will just turn into, hey, check this out. Look, oh, I've done T on both sides. Here, what I want to do, sorry, I'm getting ahead of myself and not even looking at my notes as I write. Here, I want to take the inner product of T of xy with xy. Sorry, I'm trying to show that this is positive. I'm not trying to calculate a norm. All right, here. All right, everything should be good. So let's just take xy in the second argument. That is, we'll take TV with V inner product. And so you get x plus y, inner product with xy. And here I'm just assuming this is the dot product for convenience. What's going to go on? Well, I'll get x times x plus y times x plus y. All right, cool. This isn't too much. This is just x plus y squared, which is certainly greater than or equal to 0. So T is positive. Huh. Since, I guess we should also show that T is self-adjoint. It is self-adjoint, since with regard to the standard basis 1, 0, 0, 1 of R2, the matrix of T is equal to, well, it's just 1, 1, 1, 1, right? Okay, so it's positive since it's self-adjoint and it satisfies T xy, inner product with xy is greater than or equal to 0. Do you ever see why it's self-adjoint just from this matrix? It's because the adjoint of T is equal to the transpose of this. Okay, there you go, in case that's not clear. So T is self-adjoint. Okay, nice. Now, 1 over square root 2, 1 over square root 2, comma, 1 over square root 2 minus 1 over square root 2 is a basis of R2 that consists only of eigenvectors of T with corresponding eigenvalues. Two and 0. So, with respect to this basis, T has a matrix square root 2, 0, 0, 0. After all, it's diagonal, and on the diagonal are the eigenvalues. Nice. Okay, so, nice enough. Easy. Hence, can we find what the matrix of T's unique positive square root will be? It's going to be pretty easy to tell. Yeah. Oh, sorry. This is the matrix of square root of t. I've maybe jumped the gun right there. Here. What's the matrix of t? It's this one. I've basically given away the answer. So the matrix of the square root of t is just square root 2, square root of 0, which is 0. And then we got zeros on the other ones. And this is with respect to the same basis. Oh, okay. Not too crazy. Not too crazy at all. All right. Now, with respect to the standard basis, you could compute the matrix of t and the matrix of the square root of t and so on. Nothing too hard, nothing too crazy. Okay, but let's just do it. I guess I could say, yeah, let me just start in there. With respect to the standard basis of R2, the matrix of the square root of t is just equal to 1 over square root 2, 1 over square root 2, 1 over square root 2, and I believe 1 over square root 2. Since if you just go through and you go like across and down, multiplying, you'll get 1/2 plus 1/2 in each entry, and that will give you the matrix of t. Okay, cool. So nothing too crazy at all, yeah? Hopefully at least, right? So there you go. Basically, the easiest way to do it is to find eigenvectors corresponding to eigenvalues. You know that with respect to that basis, you can write your matrix diagonally with the eigenvalues on the diagonal, where each eigenvalue corresponds to the eigenvector in the basis in order. And then to find the matrix of the square root, you just square root the diagonal entries. Bada boom. Nice. Okay, so to get back to the regular old basis or whatever other basis you want, all you got to do is use the change of basis. Just do change of basis formula, bada boom. Now you're back to the matrix of the square root in some other basis. This tells you how to write that matrix with respect to whatever basis you're using. Easy. Or you could just do it abstractly in terms of a generic basis, and there you go. You now have written the square root of your operator with respect to whatever basis you want. Cool. All right, so let's leave it there. Let's call it quits for today. I'll see you next time. Have a good one.